ECE 541 students will be using norms for some of their homework assignments and perhaps for some of their projects. So I'm going to introduce a few small topics about norms. In this case, I want to talk about norms on finite sets. What do we mean by norms and how do we define them? Well, generally, a norm tells us about the size of something. So if we're interested in finding out about something's magnitude, a norm is a way to do that, and it's a mathematical description of a function that satisfies certain properties. So you're probably most familiar about the absolute value, which is a norm. And the absolute value tells you the magnitude of which a particular integer or real value is, how far away that is from the center of the number line. So it doesn't tell you anything about its sign, it just tells you, again, how big it is. So to better understand norms on signals, which are important for the course, I want to look at norms on finite sets first, because that's going to give us a little bit more insight with a small example that we can easily hold in our heads and see how it behaves. So let's define some set, V. So V is going to be a set of elements that we can count. So it's going to be of size less than infinity. So a norm on V has to exhibit the following properties, if it's to be called a norm. The first is that the norm of V must be greater than or equal to 0. And the second, which is likened to the first, tells us that if the norm of V is equal to 0, then all elements of V have to be equal to 0. So that is, there can't be any element of V that's non-zero, or this will not be a norm. The third property is that if you have a scalar value alpha, so alpha is in the reals here, if you have a scalar value alpha inside the norm line, so alpha of V, what's the norm of alpha of V? It's the same as the absolute value of alpha times the norm of V. And finally, we have this probably fairly familiar inequality, that the norm of the sum of two vectors is less than or equal to the sum of their individual norms. So this is the familiar triangle inequality. And we use this quite frequently to demonstrate some properties of norms. So let's actually define some norms, because what we've seen so far are just the properties that a norm has to exhibit if it wants to be called a norm. So let's first of all define what we're calling the one norm. So the one norm of V is the sum of all the elements of V, but more importantly, it's the sum of the absolute value of all the elements of V. So this can alternatively be called a few different things. So one of these is the taxicab norm. So why is it called the taxicab norm? Well, if you've ever lived in a city that's laid out in blocks, like Tucson, you can't actually go on the diagonal between any of the blocks. So this kind of an operation is not permitted. So the taxicab norm tells you that I can only move along some axes. I can't actually get to the shortest distance between two lines. I have to go along these prescribed distances. So the taxicab norm is going to tell us the individual magnitudes along the axes that we're concerned with. So let's say that we have this set of 5 values in V. So the one norm of V is, again, the absolute values of each element summed together. So in this case, 13. So let's look now at the 2 norm. The 2 norm of V is the sum of all squares of the absolute value, and then we take the square root of that. So it's the square root of the sum of the squares. Now this probably sounds familiar. The square root of the sums of the squares is familiarly how the hypotenuse is defined. So this is actually called the Euclidean norm if we have a 2-space. You can think of this as a magnitude in terms of complex numbers, or root mean square in terms of a signal. So here's an example where we have V is equal to -3, 0, 4, 5, and 1. So these are the individual elements. So the 2 norm of V is the sum of all these individual values squared. And these values, again, are the squares of all, it's the sum of the squares, and then you take the square root. So in this case, V sub 2 is equal to 50, the square root of 51. So let's look at what we call the P norm. So the P norm is like the 2 norm, except instead of looking at the square of each individual value and then its square root, we look at the pth power of each of the individual absolute values, and then we take 1 over the p root. So this is basically taking 2, turning it into 3, 4, 5, as we saw in the previous norm. And we're taking the absolute value to the pth power. So for negative values of v sub I, we're going to see that that value turns out to be positive. So here's an example for v, the 5 norm of v. So we take each element to the 5th power, and I conveniently put that in my calculator and added them all up. And then we take the 1/5 root of this to give us 5.352. So this is the 5 norm of v. So first of all, we can see that the square root of 51 is 7.1414. For the first norm, v1, we actually got a value of 13 for that set. So in this particular case, we see that these values, the 1 norm is greater than or equal to the 2 norm, which is greater than or equal to the 5th norm. What happens if we take the limit as p approaches infinity? So the infinity norm is in fact the p norm where p is taken to infinity, and that converges on the maximum value of the individual elements of v. So it's the